Okay, so now having spoken about GANs in general and then conditional GANs, how to input an additional condition and additional information along with the latent representation, the latent vector Z into the generative model. But now how do we know if this GAN 1 that I have trained is better than GAN 2? Of course, we can look at it qualitatively, but then quantitatively, how do we know that one GAN is better than the other? And it's hard and an active research area itself how to evaluate generative models. The desired properties that we want to evaluate it against are one, fidelity, right? We want the quality of the images to be very high. And then diversity, that measures the variety. So we want to essentially find metric that evaluate both the fidelity and diversity. What do I mean by that? Like, what if we had like very high fidelity but no variability, no diversity, and it would almost, almost, let's say, output the same image every time. We don't want such a generative model. At the same time, we want the quality to be high and the diversity to be high. If only the diversity is high, if it's just giving us different dogs, but the quality of the dog themselves are not very high, we will not be very happy. So we want our metric to quantify both the fidelity and the diversity. For example, fidelity can probably be evaluated using just pixel difference, right? So it's simple, but it's unreliable. But we can then also maybe find the fidelity, measure the fidelity by measuring the feature distance, right? So we have two latent representations. Somehow we have our two sevens, and then we create Z1 and Z2 with that, and then we measure the feature distance. So used higher level images and thus making it more reliable, because features have some interesting, let's say, properties, behaviors. Maybe similarity between the features would mean similarity between the original images, like we have learned in the self-supervised videos. So one way to do fidelity is using, let's say, these latent representations and distance between them. Now diversity is, let's say, so this is a little bit different, but is also 8. This is definitely an 8, and this is giving us a good diversity, and this is what we are after. So, but it's not straightforward, because unlike a classifier, it's not straightforward to decide if one GAN is better than the other. And that is the goal. That is what we want to do. Why is evaluating a GAN hard? Because in a classifier, well, you get an output, a dog for this image, and you're happy, and you can qualitatively measure, let's say, a number. You can measure the F1 score, right? But when you want to do a GAN, you get an image of a dog. This looks a bit weird. The eye looks a little bit weird, but okay, it looks real. How much real? How happy I am with that? You cannot have humans, label each and every image, and that's also subjective. So how do you do it quantitatively? And the best, it's still not bulletproof, but the best idea that people came up with was something called as the Frecce inception distance. So Frecce inception distance is something very simple. Essentially, the distance metric itself, the Frecce distance. So the Frecce distance, what it essentially measures is the slack between two different ropes, right? So you can later look at this here, and he gives us this Coursera video that I've linked. And what the intuition essentially is that how much is the distance between, let's say, the minimum leash length for the dog to go that distance, right? So for example, the dog is this far from me. What is the minimum leash distance? And it kind of minimizes the distance between the two leashes, right? So how much is the distance between the two leashes? And that is the leash distance, the minimum leash length for both those cases. And how do we measure this minimum leash length? The way to do it is very simple. What you do is you create these two distributions, X and Y. Yeah. So we have these two real and fake embeddings of two multivariate normal distributions, meaning we take our data set and we create embeddings from this model called as InceptionNet v3. So if you remember InceptionNet, was used, so InceptionNet v3, and this was the ImageNet winner, if you remember, in 2015, if I'm not correct. So this was the third winner, right? So the first one was AlexNet, the second one was ZNF, Zahler and Fergus from my lab, and then InceptionNet won. So what they're saying is, you put your image into your ImageNet, both the real and the fake, and you take the vector out that you're getting, right? So the embedding vector, the latent vector, and then you so you have the latent vectors from your real distribution, you maybe call it X, and you have it from your fake distribution, you maybe call it Y, and then you compute the mean and covariance matrices of these vectors, right? So you so the covariance matrix is here, and the variance matrices are there, right? So you basically compute this Gaussian, so you can simply compute the mean of all these vectors, and that becomes the the mu x and mu y. Similarly, you compute the sigma x and sigma y, the matrices, and then this covariance matrix, and then you put it into the formula of FID. So you compute the L2 distance between the two mean vectors and the trace of the vector of the sum of this subtracted by 2 times the covariance matrix. And this is then a quantitative measure. This is a single number, 0.6. And then you can say, okay, this model M1 is better than my M2, right? So this is how one way of calculating, and probably the most popular way still, even when we are in the world of say diffusion models and whatnot, this is still one way of how we measure the quantitative distance between the outputs of two models. But note how slow it is, right? Because you have to run over the entire data set. You need to create all these embeddings. You have to run a neural network on all of that. You create, so for your data set, you can do it once because it's not changing. But the output of your model keeps changing every iteration, every epoch. So you have to be very careful how often you run your evaluation. And as you see, evaluation gets more and more complex as we start to, step into the realm of generative models. What are the shortcomings of FID? Well, we use InceptionNet v3, which may not capture all features. For example, this InceptionNet v3 is trained on ImageNet. Now, what if we want to create a GAN on, let's say, medical images, or let's say even simple things like MNIST, right? Because MNIST is trained on these black and white handwritten digits. The ImageNet dataset is not like this. So there is a data distribution shift, right? So there's a distribution shift between what the original network was trained on and what our current distribution is. And because of that, your inception model may not be the best representation. Your latent vector may not be the best representation of your original data or your generated data. So that is one shortcoming. You need a large sample size to create those, means and variances. So you need a large sample size. It's slow to run because you need to forward prop a completely different model. And finally, it assumes your model to be multinomial distributed and limited statistics. Only the mean and covariance is used. Yeah, so this is the shortcoming of FID, but still this is the best we have found till now, and this is what we use every time. And because before FID we were simply using the inception distance, and it's worth checking it out, but we don't use it, and I recommend you also look at this video.